Okay, you can start.
Hi all, I'm Beatrice Tucci. I'm currently a PhD student at Max Planck for Astrophysics, working with Faber Schmidt. And today I'll be talking about my PhD project very quickly. If you are interested, talk to me later. Basically, looking at spectroscopic surveys, we can try to extract cosmological information at the field level. And for more information, you can talk to Ivana Babic, who is presenting a very nice poster. And also to compress your galaxy density field into summary statistics. And here I'll be focusing in this approach. Mainly, I'll be using the galaxy power spectrum and bispectrum. And the question I'll be trying to answer is whether it's okay to assume a Gaussian likelihood on the large scales, because we know that the number of modes grow with k, and at the very low k mode, due to the break of central limit theorem, their distribution is not Gaussian. So, and for that, I will use SBI to get the entire distribution of these summaries. So here is our pipeline. So the idea is that basically you sample your cosmological bias and noise parameters, you evolve it with some gravity solver, and then you obtain your galaxy samples, you compress your power spectrum by spectrum, and then we use some neuron density estimator to obtain the posterior. So talking about the neuron density estimators, we are using the SBI package, so NPE and NLE, which are two types of neuron density estimators. And the cosmological bias and noise parameters, so the idea is that we only observe galaxies in the sky, so we have to make a connection to the cosmological parameters. And for that, we have to marginalize over the bias and noise parameters as well. And this is known to be a very robust galaxy matter connection on the very large scales. And how we do our gravity evolution, we use left field, which is a method based on the EFT of large-scale structures. So the idea is that we assume our ignorance about the small scales, and we just integrate out everything of the small scales, and we just do our constraints on the very large scales, where we know that all the modes are under control. And yeah, we basically use LPT to do the evolution and get at the end our galaxy density field. And the question is whether the low K non-Gaussianity affects cosmological inference. So we assume an Euclid-like mock survey. And the first step was to generate some summary statistics from a Gaussian likelihood, so using both a sample and analytical covariance, and then we found the posterior of sigma 8, which is in the first column, and marginalizing over bias and noise parameters. And then we compared it to the full SBI approach, which takes all the distribution of the summaries, and we found no difference in this case for this volume, these scale cuts, and these cosmological parameters. Of course, if you change any of those, it could be that the low K non-Gaussianity could affect your results. And also we did some posterior diagnostics, and that's it. Thank you.
Thanks, Beatrix.